My name is Erin Elisha and I'll be starting with the concept of crystals. An ideal crystal is a theoretical structure where all atoms are perfectly arranged in a repeating three-dimensional pattern. However, in real life, materials are real crystals, which means they contain defects or interruptions in the crystal lattice. So why does this matter? These defects are not actually failures. Instead, they are very important because they affect how a material behaves. Crystal defects also helps to determine the mechanical, chemical, and also electrical properties of materials, which is why they are very important in engineering applications.
Hello everyone, my name is Manuel and I will be discussing about the classifications of crystalline imperfections. In nature, atoms in crystal lattice don't always sit in perfect rows. These irregularities are what we call defects. Generally, we categorize them based on their geometry. The first one being point defects. These are zero-dimensional flaws, such as a vacancy, where an atom is simply missing, or an interstitial, where an extra atom is squeezed into a space it doesn't belong. Other than that, line defects. These are one-dimensional defects, most commonly known as mixed dislocation.
Next, I will be presenting about point defect, focusing on vacancy defect. A vacancy defect occurs when an atom is missing from its normal position in a crystal lattice. Even in a perfect crystal, vacancy can still exist. Vacancies are formed due to the temperature effect. At temperature above absolute zero, atoms vibrate around their lattice position. When the temperature increases, some atom gains enough thermal energy to leave their lattice sites, creating vacancies. Therefore, vacancy defects are thermodynamically unavoidable. After that, vacancy defects have several important effects on materials. Firstly, they provide pathway for atomic movement through diffusion. They also contribute to creep deformation, especially at high temperature. After that, the presence of vacancies causes a slight decrease in density and reduced electrical and thermal conductivity. When many vacancies combine, they can form void, which may weaken the material. To sum up everything, vacancy defects play an important role in determining the mechanical and physical properties of material.
For this slide, I will be explaining interstitial point defects. An interstitial defect happens when an extra atom goes into the space between atoms in the crystal lattice instead of replacing an existing atom. There are two types of interstitial defects. The first one is self-interstitial, where an atom from the same material moves into an interstitial space. The second one is impurity interstitial, where a foreign atom, usually smaller, fits into the empty space between the atoms. These interstitial atoms disturb the normal arrangement of the crystal structure. Interstitial defects can affect the properties of a material. They can cause lattice distortion and increase internal stress in the material. Because of this, the material usually becomes harder and stronger, but the ductility can decrease, meaning it becomes less flexible. Interstitial defects can also change mechanical and electrical properties. For example, in steel, carbon atoms occupy interstitial spaces, which increases the strength and the hardness of the steel.
Next is line defects mixed dislocation. So what exactly is mixed dislocation? A mixed dislocation occurs when a single dislocation line within the crystal lattice exhibits both edge and screw components simultaneously. Essentially, it is a hybrid combination of the two. The most interesting part is that different segments of the exact same dislocation line can behave differently depending on their orientation. Because real crystals are complex, mixed dislocation are actually the most common type found in nature and engineered materials. Next is effects on properties. The first one is it can control the plastic deformation. Second, it affects strength and hardness. Third, it can scatter electrons which would reduce the conductivity. The fourth one, it acts as a diffusion path for atoms. And lastly, it influences ductility for materials. As an example, they are found in almost all structural metals, such as steel, copper, and aluminium. And they are extremely common in deformed or cold work materials.
Crystalline imperfections are small defects found in real crystals, so even they are tiny, they have a big effect on material properties. First, mechanical properties. Defects block the movement of atoms, making materials stronger and harder. However, too many defects can make materials less flexible. Next, chemical properties. Defects are high energy areas, so chemical reactions happen more easily. This causes faster corrosion and oxidation. For electrical properties, defects disturb electron flow and increase resistance. In semiconductors, defects are added on purpose to improve performance. Defects also affect heat flow. Materials with more defects transfer heat less efficiently. Finally, defects help atoms move inside materials. This process is called diffusion and is important in alloy making. In conclusion, no crystal is perfect. These defects control how materials behave in real life. So, by understanding them, engineers can design better and stronger materials. That's all from me. Thank you. Snowflakes form crystals, but when they pile up, they are no longer perfect. This is similar to crystalline imperfections, where the crystal structure is not ideal.